to participate in this workshop and to present here. I want to present about joint work with colleague Per Broberry from Lund, adaptive dose finding with power control. And the work is motivated by a real case study from a consultory work, whereby I won't come into the specific details, but I think I'm very close about the essence of the problem I'm presenting, and yeah, also sizes of the study are quite close to the to the real study. So it was a demand for designing a phase 2 trial for a new drug, not in oncology, in another indication where you in phase 2 often have two desires to prove that the drug has effect, and then at end of phase 2 to perform a dose finding study to prepare for phase 3 then. So in this situation, the treatment effect of the drug, which I denote by theta, was uncertain. There was some good evidence that the drug should work, but nevertheless some risk was judged that there's no effect of the drug also. And then for this phase 2 study, it was also desired to investigate then the dose response curve. So by several doses. But the client had limited resources, so they've seen that there, in some cases, there might be a balance by between two aims: the aim of showing an effect and the aim of investigating the dose response curve. So yeah, but before I come to the dose finding case study, I want to start with a quick review of sample size recalculation, which I will later need to apply in this dose finding case study, talk about usefulness and some problems identified with sample size recalculation. And then afterwards I come back to the dose finding case study I mentioned. So sample size recalculation, which was proposed if you have uncertainty about the effect of a drug in a simple setting. If you have a two sample case, so control and the new drug to compare, and you want to test the null hypothesis that there's no effect, theta equal to 0, versus that there's a positive effect. When you have a normal assumption and I assume common known variance here, then you have the familiar sample size formula like shown here, and then you know you need to specify the parameters sigma, and now I want to focus on the effect theta. How should theta be chosen? Sometimes you have motivation by clinical minimal effect, clinical meaningful effect, but in other situation one has some interval of interesting theta values, and it's a judgment how large should the study be. So if the effect of theta is if we would know or anticipate that it's very large, then we see that we can run a study, a very small study here, since we divide by theta square. And now from the investment perspective for the company, yeah, one does not want to invest unnecessarily much, so only if the effect is small but still meaningful, of course, then a larger sample size is justified. So when then theta is smaller, then our n becomes larger. So yeah, the idea then for the sample size recalculation is to calculate an initial sample size n null based on a rough guess for theta, then perform an interim analysis after a certain number of patients, and we come back to it also how early or how late this interim analysis is meaningful, and then to recalculate the number based on the interim estimate. So as an example, which I later will not use, but anyway as a natural example for recalculation rule would be to plug in then the interim estimate in the sample size formula. So you have here the same formula as before, and in the interim analysis you estimate the treatment effect and update the sample size, recalculate the sample size then to this value, and I write here capital N, since we have then a random variable for the sample size. So if I want to use the blackboard here, then yeah, this formula here would then mean, so if we didn't, yeah, thank you. If we draw the sample size dependent on the estimate of theta in the interim, then this formula means that we have 1 over the estimate to the square. So some sample size curve looking this way. And then yeah, in practice we cannot do too large studies, so we have limitations here in this context. First of all, also investment bounds. So therefore we would have an upper bound for the sample size for if the interim estimate is below some value. We would have this sample size, and then we would follow the formula, and if it's above some value, we would have a minimal sample size. At least we have to the minimal sample size of the number of patients before the analysis, of course. So this as a natural sample size recalculation rule, which as mentioned, I will not use this exactly this way. Instead, I will derive here another possibility. But as many of you know, the sample size recalculation has impact then on type 1 error, or if we start before, on the distribution of the final set value. So it's no longer, if we compute the usual set, it's no longer n standard normal distributed. So then the test, which I called conventional test here, to reject the null hypothesis at the end of the study if the final set is above the conventional critical level, might not control the alpha level. Can understand this by thinking what happens under the null hypothesis. Under the null hypothesis, when theta is 0, then we might by chance anyway have a positive theta estimate in the interim analysis. If we have by chance a very high positive theta estimate, our sample size will be low, and maybe if this is already the number of observations before the interim analysis, then we will stop after the interim analysis and stick to the optimistic, to the high value of theta, and so reject probably the null hypothesis. But if we have small values of theta in the interim analysis, then we run a very large study afterwards where where the first part of the study does not play much role. So this together gives then that in certain situations, even in practically relevant situations, not only in constructed situations, that the type 1 error can be considerably higher than alpha. So here one example, 7% instead of 5%, so but you can construct much worse situations. This was a reference for a practically relevant situation. So this we have, and then it was mentioned before already that you can deal with it in Chris' talk. So you can then compute set values from both before the interim analysis and after the interim analysis, and for example apply pre-specified weights to the set values, which so you weight the stages in a pre-specified way, which in turn means that you weight the observations differently in the before the interim analysis and after the interim analysis. But then you can ensure that you have then, if you apply this method, that you ensure the control of the type 1 error. So and then other possibilities exist. For example, that you keep the conventional statistic here, but you adjust this value. So you can deal from the statistical mathematical perspective easily with it. There's no issue, and but anyway, from a practical perspective, I mention here that it would, if there would be the possibility to anyway use this conventional test here, it would simplify the communication in practice. So, and when I mean possibility to use it, then I mean if we can now prove that this test controls the type 1 error in a specific situation, then it's a huge benefit from the practical perspective, I think, even if statistically you might not see so much benefit, since you have well-developed methods also. So, and but for the in practice for the communication, it's often then so that the people are used to the conventional tests, and if you then if you apply another test, you run the risk that someone else applies the conventional tests, and in the worst case they give different results, which we understand and we can argue and have the arguments, but anyway you need to then, in the worst case, to have extensive discussions. So if you can avoid it, it isn't benefit, but I'm not saying that you have to avoid it. So I'm not saying that your methods like mentioned here or other related methods are necessarily to avoid, but it's only just mentioning that if you can avoid it without much compromises, then you have some advantage. So then other things related to sample size recalculation is that in practice we have then some more problems in the logistics. People are then used when running trials that they plan and pre-plan how many patients in which sites to recruit, and if you only can tell we have some limits here in the sample size between this and this value, then it makes it much more difficult for the people conducting the trial. And further, another criticism to sample size re-estimation is that the interim analysis should be done by an independent committee, not communicating any results in the best way. But if they have to communicate then the sample size, the final sample size for the study, and so if it is known that you have such a yellow sample size rule, and the sample size here n star is communicated, then people can back calculate that the interim estimate was of a certain amount, and so it's no longer confidential interim and information. So this has been identified as some drawback for applying the method, and we keep this in mind. But on the other hand, the sample size recalculation has the advantage of better power control. I will also specify this more in detail, power control, what I mean with it. So, but now after this general word sample size re-estimation, coming back to the problem of the case study. So this is the slide we had in the beginning. So the treatment effect is uncertain, and the desire here to investigate a dose response curve. The basic idea is that to run what I call a seamless phase 2A/B trial, where I mean with phase 2A approve that a drug works, and phase 2B then a dose finding study. And so the basic proposal for the study was to start in phase 2A or stage 1 of the trial with placebo and one dose of the new treatment, and then in an interim analysis to analyze maybe if there's really no evidence for drug effect, then we would stop for fertility, and in stage 2 then perform a dose-finding studies with, in this example, 3 doses and placebo. So, from the investment perspective, when thinking about what about the study and about the interim analysis, so the dose-finding part is usually larger. So we want to have some proof of effect before going into the dose-finding part, and only justify to run from an investment perspective to run this phase 2b part if there is sufficient chance of success for the drug. So therefore, we could require a certain conditional power of success for the final analysis before going into phase 2b. For example, some a conditional power, which I denote by 1 minus gamma of, for example, 70%, as a requirement to invest then in the second part. What I mean with conditional power, some of you are very familiar, but I will anyway briefly define here what I mean. So, and conditional power is not now specific to sample size re-estimation, and a general concept which you can, for example, look in Chris Jennison and Turnbull's book, described conditional power. So we would here then in the interim analysis be interested in the probability to reject the null hypothesis at the final analysis given the interim data. And then we have given the interim data, but we still have this unknown parameter theta of the treatment effect. So the conditional power in its first version depends on the unknown parameter of treatment effect. And you can then express this for normal distributed observations, can express the conditional power this way, where you see here you have the dependence of the unknown theta and also the nuisance parameter in this case. But we have to make a decision then in the interim analysis. We want to have some specifiers of 70% conditional power. What do we use for theta? We could use the theta for the initial planning. Another possibility is to calculate the conditional power at the observed interim theta. And then, so we rely on what we have observed in the first part of the study, and use this observed theta here, and so we can then derive that the formula becomes much simpler and is then independent of both theta and sigma, such that given a certain interim observation of the interim set value, we can compute which conditional power we have to be successful in the end. And then you have here this is the time of the interim analysis, N1, the number of observations before interim analysis, and N2 the number of observations after the interim analysis. So this is then the fraction of observations before interim analysis. And so I will use this conditional power at observed theta later, but I want to also anyway mention that another important concept is predictive power, where you not rely on the point estimate of the in the interim analysis, but you take the likelihood of the interim data for theta, so you have a distribution around the observed theta, and integrate then the conditional power over this likelihood density, which defines then the predictive power. Or you could view this as starting with a non-informative prior before the study, and then having in the interim analysis a posterior distribution here. So and also here you have then a different formula, but independent of theta and sigma. You could use predictive power, but I want to use then conditional power based on the observed theta. And so I've shown this basic idea for the design. We have here then N1 patients for each placebo and dose A. And in the second part, I specify the design in this way that we have then N2 patients in placebo and dose A. And for dose B and C, we want to come up to the total number in the other doses as well. So these will be then over-recruited or recruited with a higher allocation rate to come up to N1 plus N2 patients. So in the interim analysis, we compute a set statistic, and then in the final analysis, we compare also as a main comparison, which I focus on the dose A with placebo, and have here then until the total sample size here N1 plus N2, the set statistic. So in terms of conditional power, then the conditional power to be successful for this fixed design so far is such a curve here for a certain example. So if we have a target of 70%, then it would mean that the recommendation based on conditional power would be here to only go to the second stage if we have a set value of in the interim of 1.76 to ensure this conditional power, which corresponds to a p-value of around 4%. So this might be a too high requirement. So what can we do about if we have in the interim a conditional power in this area where we are below 70%? And below 70% would mean that the treatment effect seems to be lower than anticipated. And so we would think about now to apply sample size recalculation to increase the conditional power. But then it's important to reflect what does this mean now for my dose finding issue. If we have an effect which is lower than anticipated, it might be not as important to investigate doses below the dose A, which dose B and C were intended to be doses below the A dose. So then the dose finding task might be less important. And therefore, it could be reasonable to, if the conditional power is too low, drop dose C or even both dose B and C and distribute the patients then on the remaining doses. And by this we will see that we can increase the conditional power. So this is now the first part of the study. We have the interim observation, and if we have a large enough interim observation for Z, we have conditional power is okay. We go to the planned study. But if the conditional power is lower, that Z is lower, then we would drop dose C and distribute these N1 plus N2 patients from C to the other doses, such that the sample size here becomes this value. And if we are even lower here in this area, we would even drop dose B and have then sample size N1 plus 2 N2. So this means in this case we have fixed number of patients in total, which you can calculate. But for the test, when we compare dose A with placebo, we have a flexible sample size. So this means in terms of this test for comparing dose A with placebo, we have some sample size recalculation, even if we have a fixed total sample size for the study. And and then I also add, now I've not mentioned so far, so if the Z value is too low, we will stop for futility, the study, which is important part here. So we would now like to, if it's possible without losing too much, we would like to use the conventional test in the end. But we have seen we have some hidden or open sample size recalculation here in the design. But it has been identified earlier that in some important cases the type 1 error is controlled with the conventional test, and my colleague Per has provided some explicit bound when you are safe and the type 1 error is controlled. And you see here a formula when the interim Z value is above this value here, depending on the time of the interim analysis again, and how much you raise the sample size, this V. Then if this is fulfilled, then there's no issue with you have the type 1 error controlled with the conventional test. So in our case, we raised the sample size from this value to either this value if we drop dose C, or this if we drop both dose B and C. Then we can calculate these values. And I calculate this for this example, which is then close to the real case study, where we have 70 patients in the first stage in each group, and then a goal of 120 patients in total for the whole study, such that we have these numbers. And for this we, it's now the same as we had seen before, but now with the calculated values 1.4 and 1.31. If we have a Z interim above these values, then we can raise to this sample size, or if we have above this value, we can raise to this value. And then we had the other aim to keep the conditional power above 70%. So we can then calculate that if we drop dose C and distribute these patients, then we need at least 1.56 in the Z interim to ensure this conditional power, and 1.30 if we then distribute all the B and C patients. So and we have seen the type 1 error is controlled as we are here above 1.41. If I back to the 1.40 was the result here. So in this case we have controlled the type 1 error, and here we know 1.31, which is almost the value here. So therefore, if we use these bounds, and here maybe 1.31, so the maximum of the with the value shown before, then we are safe with regard to type 1 error control. And then our design would look like this. So in the interim analysis, we calculate a set value and have then these boundaries corresponding here to p-value of 4%, 6% I think, and 10% for going choosing one of these possibilities then in stage 2, and then we are allowed to use the conventional test at the end with the final set value of 1.96, even if we have a flexible sample size for the comparison between dose A and placebo. The conditional power then in the interim looks like this. So we have the observed set value from the interim, and if it was above 1.76, we continue with the design we had planned. So we go to a 4-arm trial. If it's here lower, then we run a 3-arm trial and increase the conditional power, still ensuring that it's above 70%. And here, if it's below this value, the interim observation, we go to the 2-arm study. And if it's too low, we stop for futility, and we have no conditional power to be successful. So this was for the fixed study, the conditional power, if we don't change anything in the interim analysis. And and the sample size rule then, when we look at what is the sample size now for dose A and placebo, so the total sample size is mentioned is constant, but for these doses, depending on the interim observation, it is this curve. So here you don't change anything, you have the specified sample size of 120. Then here you increase to 160 or to 240, or you stop in the interim analysis. So you have not this sample size rule, but some similarities here in this right hand part of the, that you have some step function here instead. I skip these and as a summary, so we can increase the conditional power to a reasonable size, like we had here in the example 70%, in such dose finding studies, with the trick that we gradually switch from the dose finding objective to focus only on effect proof. If the effect turns out to be lower than anticipated, we take all the patients to for the one comparison of dose A to placebo, and it is from practice also justified, since you don't want the importance for investigating lower doses is lower if you have a smaller effect. Some of the important practical limitations for sample size recalculations are avoided, so we have a fixed total sample size, not the issue of back calculating, therefore. Example, and yeah, you can here in some cases also use the conventional test at the end. And what is important is that it is not too complicated to design. It's feasible to conduct a study, a similar study we had previously conducted at AstraZeneca, not with sample size, this sample size re-estimation part a bit differently, but from the logistics with the same demands. But still, the logistics are more complicated compared to a fixed design, as you have to prepare then the allocation rates to the doses in a flexible way for stage 2. So this makes it more complicated. One has to acknowledge, and that the allocation rate to placebo can change during the trial is sometimes criticized, yeah, so this might be a discussion point for this design. But generally, yeah, you can view this that you have a fixed sample size, so a fixed total sample size, and you can use the conventional final test for this design. But so this is the outside of the box, and inside you have adaptive design where you have sample size recalculation and conditional power control, so some more interesting adaptive elements. But yeah, from an outside it looks like some fixed design which can have some benefit. So thank you for your attention.
Okay, thank you, Frank, for this nice talk and giving us an inside view in the box. And now, do you have any questions? Frank.
Frank, have you compared the power curve of your procedure, where you insist on using the conventional test statistic to the combination test approach proposed by Christian in the first talk? Because your design only works because you are essentially switching from one design to another one where the conditional error is smaller, so which means you don't exhaust the level out. And it has been criticized by many people like Eckhart Grimm. That's an inefficient design. So how much is the power loss by insisting on using the conventional statistics?
Yeah, so I can only now give a small insight in the type 1 error I've looked at for this example, that it is slightly below the alpha. Instead of 2.5% one-sided, it was 2.45 or something. So it was not tremendously conservative in this case. So yeah, for yeah, so there you have to do some. If the futility analysis introduced, the alpha reduces more, but for this value I mentioned, I have deleted the futility analysis, and then it was not too conservative.
Related question. When you're using that approach, you're constrained as to when you can change the sample size, because there are values of theta hat which are too low for any increase in sample size to fall within that condition that you mentioned. But you could go further into that domain if you stop saying, well, we want to use this conventional analysis and do a combination test. Have you explored that at all?
How do you mean if the zeta is maybe too lower than the 1.3 or something? You would.
Yeah. I'm just thinking, because you mentioned the Meta Pocock paper, and they define a promising zone when they can do
Yeah.
what you're referring to. And my experience with that design is that actually I want to increase sample size in some other places that they won't let me. But a combination test does allow you to do that.
So then you would ensure that the type 1 error control by another method, like the combination test. The question is, and as I mentioned, I see the use of the conventional test not as a must to all. It's always a balance. If it's only if you don't lose too much on the other end, it has some benefits. But if it's in such a situation, if people would say that for this value we won't like to stop the study, then we have to find a way to deal. What do we do if the theta estimate in the interim is too low, and if and then we have the methods which are well described. So what I wondered is whether you should combine it, some combination, so only to apply the combination test for certain interim results, but yeah.
Okay, one short last question.
Okay, so if I was to do a typical phase 2A and then a phase 2B study, and my initial study showed that I had a smaller effect than I actually thought there would be, one thing that I might think about doing is raising the dose, increasing the dose. Would there be any problem with, if the effect is too small, to have larger doses in a second stage?
It depends certainly on the situation, and sometimes you have some upper bound of the dose in advance and you don't think about this. But if you have a situation like you're mentioning that it's possible, it would ideally would be good to think about it in advance, of course, to prepare for this possibility. Now theoretically to apply this design, I've only written those B and C. The B and C could be higher, so the same type 1 error control would be valid. But on the other hand, if in such a situation, one would perhaps think in some details here differently, and so you would then in this situation not try to delete dose B, but to have the dose B then above, and so you can do this, and then you can you have to rethink what happens for the implicit sample size re-estimation you're doing by another design definition where you add an upper dose here, since you change the placebo number of patients maybe, but then your final test would be then the main final test would be dose B versus, or this higher dose versus placebo, and so you have to think about the multiplicity issues then occurring, but but I agree that it would be then in these situations a reasonable thinking to add a higher dose.
Okay, thank you. We thank Frank